Let's get started. How is everyone? You know why you're so excited? Because it's a goodie bag day, and I'm not going to deny you a weekend of goodie bag action, which is why you're getting it today. Even though the topic in the goodie bag is crystallography, we will not start talking about crystallography until Monday. But I didn't want to wait. I know you didn't want to wait to have these models in your hands because it's an enhancement of your weekend activities. So the goodie bag, again, just sort of like last time, I'm giving it out to you today, but the topic will start on Monday. Today, instead, we're going to talk about metals and metallic bonding and the properties of metals that are related to the kind of bond that you get in metals. And, you know, we kind of motivated band theory of solids with conductivity, and we talked about conductivity. There's a chart of conductivity, and there's some elements in there, some elements in some materials that are more complicated, right? Like glass isn't necessarily one element, or silica. There's diamonds, silicon, germanium, copper. And we talked about insulators, semiconductors, and I've mentioned metals, and that's what I want to focus on today. We did this in the context of the bands, right? So remember, here you've got your conduction band, and here you've got your valence band, and the valence band is filled. And so if there's a large gap, that's the gap. If it's large, like, you know, over 3.5 eV, then it's an insulator. And then the one in between we talked about a lot on Wednesday, that, you know, if this is your gap and it's, say, between, you know, 0 to 3.5 EV, then that's a semiconductor. And so, you know, that's what we talked about. That's in your goodie bag. We talked a lot about semiconductors. And then we talked about how, well, if you have some kind of band that is filled in the middle there. So it doesn't have to be filled in the middle. It could be filled here. It could be filled up here. But the point is that the filling of electrons does not stop where there's a forbidden zone of states, right? Where there's no states. That's what this is. That's what a gap is. It's a gap of electron freedom, right? Whereas in a metal, there is no such thing, because you fill up to a point where then right above that infinitesimally tiny bit of energy away, there's a free state, right? There's a free state. So you're in the middle of a band, and that's a metal. Well, I mean, this is, you know, so we should say the gap here has to be greater than 0. Here, the gap would be equal to 0. There's no gap. You can't define a gap in a metal. And we talked about semiconductor problems. I looked up, just for fun, you know, I mean, why not? Because most you do it late at night. You look up old exam problems and you play with them. And, you know, okay, so from last exam, right, so this is for the semiconductors. We had, oh, here's a good question, 2.8 centimeters cubed of pure germanium. Now, I want to highlight this because there's one more thing I want to say about semiconductors before I move on. Now, it's doped, and that's what we spent a lot of time talking about on Wednesday. It's doped with 50 micrograms, okay, of selenium. That was the problem. And the first part of the problem is how many carriers are produced. What? And in the same question, it's like, are they N-type because N-type, or are they P-type? What type of carriers? Those are things we can now answer based on what we learned on Wednesday. And so, you know, then you have this, and you say, aha, I know where to start, because everything starts here, right? And so pure germanium is doped. Well, first of all, where am I? This is my map, right? Germanium is there. And now, it's doped with selenium. Is selenium to the right or to the left in the period? It's to the right, right? And so right away, you know if you put a selenium in there instead of germanium. So if you take your germanium atom and you put a selenium atom in, it's gonna, if it's a dopant, it's gonna be in the bonding network that germanium was, but add electrons to it if it's to the right, right? And so you know that it's gonna be an N-type material. And if you do the math, the number of carriers is equal to 7.6 times 10 to the 20th per centimeter cubed. Now, here's something important. That is twice as many selenium atoms. Twice as many, because it's 2 over from germanium. So it had 2 extra electrons for each dopant atom, right? So the way you solve these problems, you figure out how many selenium atoms are there per centimeter cubed, and how many electrons for each of those acted as a free carrier dopant. As a dopant, remember, dopants simply give you carriers either up there, if it's N-type, or down here, if it's P-type, okay? And this is N-type. N-type. Okay, so that's a nice, now, the reason I want to do this is because, again, it is, you can never have enough fun doing problems like this and looking up old exams and stuff. But I also wanted to go back to this picture that I drew for you on Wednesday. Okay? So this picture was of the number of carriers. And remember, these are electrons that carry current, right? And we sort of drew something that looked like this. Now, remember, this is, right? These are thermally activated, and this is thermally activated, and these are from dopants. Now, we talk about this. If I put dopants in, then I can get you a constant number of carriers, because it's just defined by how much of the impurity I mixed in. How much impurity, and I can control that really carefully, which means I can control the number of carriers, and then eventually thermally excited carriers will just start to dominate. But this ability to dope with chemistry is what enabled the semiconductor revolution. Now, you say, okay, what's going on over here? What's going on in this part here, right? Well, you know what's going on there, because we drew this picture on Wednesday. Because if I have an N-type, if that's my VBM and that's my CBM, the way this works is you introduce a donor level, right? That's how doping works, right? The electrons from selenium go into here, and then you have enough thermal energy to get them up to there. And that's where they're free carriers. That's where they can carry electricity. And so at a certain temperature, below which, right, at a certain temperature, if you're lower than that, well, there's not even enough thermal energy to get from here to here, right? Not even enough to do that. So it's got to go down eventually. That's what that part is. And then the one other thing I want to say about this plot is that we have names for this. These are called intrinsic carriers, intrinsic, and these are called extrinsic. Well, I mean, that kind of makes sense. That's actually a pretty good way to name them. Because, you know, intrinsic means I didn't need to do anything. It's that pure germanium. Pure germanium, intrinsic. I didn't do anything to the material, okay? And so, but it's still, you can get carriers from thermal activation above the gap. Whereas if it's extrinsic, it means I did something external. I added dopants. Those are extrinsically doped, okay? So those are just important distinguishing factors. Now, I'm going to come back to this plot later. I want to talk about metals. Metals are all the way over here. Those are semiconductors, and doping them or thermal activation gets me carriers, which gets me this conductivity range. But metals are much, much, much higher. Right? Metals are much, much, much higher. Why? What is going on in metals that's so special? Okay, well, the way we understand everything is from the bonds. So what is happening in a metal? There's aluminum, there's aluminum, there's aluminum, and there's aluminum. For us, this is all we see now. We don't see any of this anymore. We only see atoms and electrons because those are the building blocks, right? Those are the building blocks. And the thing is that if we write down all the orbitals of an aluminum atom, there's the core, there's the shell, there's another shell, there's these ones out here, way out here, right? In the case of aluminum, 3 of them that are really, really kind of weakly bonded, right? They're way out there. They're loose. They have the ability to come off easily. We talked about this in the context of other properties, right? The polarizability, the electronegativity, right? All of this feeds in. Everything is determined by where these electrons are. And then also, as I mentioned, by how the atoms arrange. That comes next week. So, but if they're really, really kind of almost free, then you can kind of picture it like this. Let's dial it back to sodium. And you can kind of picture a metal as truly free electrons, right? They're truly free. They're in the middle of that band, and they've got all this freedom because the states are free all around them. And they're basically not really that attached to any one atom or another. And this is really the picture of the metallic bond. So let's go over here. And they're so free when these atoms come together with those very, very loosely bound outer electrons. Those electrons are so free, we actually call it a C. We call it the electron C. It's a simplified way to think about it, but it's a good picture to start with. So in metals, you've got this electron C. Electron C, we'll call it a model because it's a way of thinking. And in this model, you've got a positive charge nuclei. So you've got positively charged nuclei. Why? Because they've lost an electron to the C. They've lost it. Those outer ones have gone. Well, they're not gone because there's others around too, but they're all just kind of roaming free. And so you're left with these positive charges, right? And these are the cations. Positively charged nuclei are cations, right? And they're in a sea of electrons. And so this is because the valence electrons is not tightly bound. This is what I've been saying, but this is why you get it. Cations, so positive charged nuclei, these are cations in a sea of electrons. Now, so if you think about a metal in this way, you understand a lot of the properties of metals. This is a very useful way to think about metals. And let's go back to our pictures of bonding. Let me use this board here. We'll put it right under here. And we're going to finish what we started. We're going to finish what we started. Because remember, we talked about covalent, we talked about ionic, and then we did all these intermolecular forces and the bonding that comes about from those, but we didn't do metallic. So if I do covalent over here, and I do ionic over here, well, okay, covalent we know, right? These have maybe HH. That's a covalent bond. That's a nonpolar kind of covalent bond. Carrying is sharing. Oh, you could have HF, right, where it's sort of like, it's a little less sharing, but it's still a covalent bond. It's a polar covalent bond, right? I mean, now in the ionic sense, you have sodium chloride. We did that example where you literally, chlorine is like, gimme, and sodium is like, okay, and that's it. That's the relationship, right? But see, now here, let's take sodium and let's just put a bunch of them around. Well, but see, if I've got an electron C, then my electrons are simply wandering around in this C. So every ion has this kind of ocean of electrons around it. They're not attached. It'd be like if you say, how are you going to parent? Well, I'm going to parent, I'm going to tell, you can only go into the backyard and play. That's it, right? You are confined to be in the backyard. And now you say, well, okay, but now if I'm a proton and I'm parenting an electron, I say, you know what? You can be in any yard. It doesn't matter. Don't even come home. I don't care. Like, another kid's going to come into my backyard at some point. So it's all good. That is the relationship of a metal, inside of a metal. Maybe here it's like the two houses switched kids. I don't know what's going on. No, one of them just took the kid. But anyway, all right, I'm going too far. But here's the thing. I want to give you that sense that they're just roaming around in a sea. They're roaming around. They're roaming around. Now, here's the point. I've got a sea of electrons. We can finish our table. I'm going to finish that table. We started the table. Let's finish the table. Because now if I have metallic, all right, and I have this kind of, this kind of setup here, right? That's the picture. That's the model. And here I have cation. Remember our table? / delocalized. Delocalized electrons. And the bonding strength for this table in kilojoules per mole is 75 to 1,000. It's a big range. We'll talk about that. And there's an example, iron. We finished our table. That's it. That's the last century. Now, remember, this part of the table was the basis of attraction. Remember that? And we filled this out for all the other types of bonds. The basis of attraction. Now, I want to point out that every single basis we have covered involves the same thing. Understanding what electrons are doing. What is the electronic structure? That's the fundamental principle of this class, right? That's the key component, the key ingredient that's in all of our recipes. What are those electrons doing? That leads us to every single one of those kinds of bonds, including metallic. All right, so now you can imagine how this controls the properties, right? Now, but first I say, well, if I had a group 1 metal, then I've got one, right, like sodium. But if I go over to magnesium, you can see that I've got a higher charge because both of those electrons are likely to leave and wander around in this sea of electrons. So that would be what magnesium looks like in terms of this electron sea model. But the thing is that this sea, this picture, is what helps us understand the properties of metals. And that's what I want to talk about. And these are some of the properties, right? You can go through metals, and there's a whole range of properties. But these are some of the ones that are pretty consistent. They are reflective. They're shiny. There are literally settings in like photo apps. Metallic. Make it look metallic, right? Well, because metals are shiny. They have luster. Why? They have high electrical conductivity. That's the thing we talked about a lot already. They have high thermal conductivity. I'll mention that. High heat capacity. They're malleable and ductile. All of these and many more properties of metals can be explained from this one simple picture of the electron sea. From this one simple picture. Okay. So let's start. So if I think about, let's look at these top three. Okay. So I'll start. Why is a metal shiny? Why is a metal shiny? Well, it goes back to the thing we've been talking about all along. Or certainly in a lot of parts, right? The Bohr model and the atoms and electrons getting excited, the semiconductors and LEDs, right? It has to do with how photons interact with the material. But see, now I've got these electrons that are sitting out there at any energy level, ready for the photon. There's no gap, right? So I've got electrons sitting around in the sea, and they're ready for anything. Any kind of energy that hits them, well, they've got room to be excited. right? They've got room to be excited. And it's that, combined with other things, but it's that is a big part of why metals have their shininess. Those electrons can be excited in almost any way, right? Because there's an infinite number of states right there. There's no gap, right? So the way they can respond to energy from photons is extremely diverse. And you can imagine if I'm a photon and I excite an electron, it doesn't matter what the wavelength is, that electron can fall back down and re-emit the same energy photon, right? Okay. So that's luster. By the way, but now you know. And you really should do this. Well, look at, I just said, you have this. I've got electrons. I shine photons on these. They might come up and go back down at any, there's all this room here for electrons to be excited. There's no gap. Whereas in diamond, I've got this huge gap, right? Remember, diamond is an insulator. Diamond has a gap of 5.5 electron volts, roughly. Now you know why diamonds are transparent. It's, of course, the electrons. Of course. Because if I shine photons on this, and those photons are in the visible, you know that even if I go all the way up to purple photons, they're not that high. So anytime I try to, so I'm shining photons on my diamond, and those electrons are like, can I go here? No. Can I go here? No. Can I go here? No. You have to shine a very high energy photon to excite an electron in diamond. That's why it's transparent, right? That's the reason. When you go to the store to buy diamonds, you should ask them about the electrons. That's what's making it all work. That's what explains the properties. Okay, but back to metals. Now, okay, so that's luster. What about electrical conductivity? Well, it's the same thing. It comes from the sea. It comes from the sea. Now, if I take a wire of copper and I look at this as a sea of electrons, so I'm not drawing the ions. They're in there. I'm just drawing the fact that I've got this sort of ocean of electrons that are fairly free, right? Well, what is happening when I try to move them? The way you do it is with some kind of electromagnetic force, right? Some kind of force. And what that means is that I have a charge that this doesn't like, right? So like it's a repulsive charge over here. It's going to push one of these into the other one. But then that's going to feel a force is going to move, and then that's going to push this one, and that's going to push that one, and so forth. That's how electricity works, right? Okay. So the actual movement of the electrons could be slow in the material, but the current, right? You can push a lot of current through, right? Because these ones over here feel pretty quickly the forces you applied over there. But they only feel it. They only feel it if you can get this freedom. If those electrons are not free, they're going to feel this repulsion. They're going to be like, you know what? I'm stuck in my state. I'm stuck in this full valence band. I got nowhere to go. Sorry. Put your energy into the atom or something else. I don't know, but I'm not moving. But if it's a sea, then you can push them, and they can push each other. Right? And that's the same thing. It's a conceptual picture, but it's the same thing as almost an infinite number of free states. That's what that means, right? That's what that means. Now, if you got copper, we see copper now as something like argon with those d electrons filled, 3d10, and an s electron here. And so if it's a copper wire, those d electrons, it's all filled up in there, and they act as a way of shielding. It's a beautiful shielding so that this is even more free and less interested in staying around. So copper is such a great conductor, and that whole column is such a great conductor. And this is, by the way, such a good thing to do on a Friday night. I'm so glad it's Friday. Look at this, ptable.com. Huh, you could spend hours on this. I do spend hours on this. Property, electrical conductivity. And then it shows you like dark green is high, right? Dark green is high, and then like no coloring is low. And then you can just click around. You just click around. I could do it now, but I would never leave. But you go there and you can click on different properties and see the trends in the periodic table, and it's a beautiful thing. And you now can understand them because of the ways in which electrons behave. So you can see, look at this, there's copper, right? So there's copper, and below that we've got silver and gold, and this is a really high set of elements, right? The electrical conductivity in these three elements is super high, and this is why. Because in each case, you're going down, but you're filling the D's. Oh, and then you're even filling F's. Screening, further away. Really free S electrons. High conductivity. Electron C, right? Very easy to push them around. Now, okay. This also goes back to this picture. Because remember, I snuck it in because it was on the graph and I didn't take it out. But there was a picture of silicon where I showed silicon increasing its intrinsic carrier concentration with temperature, and on top of that was a metal. I think it was tungsten. Now, if you draw the metal, it would be way up. It would be way up, right, here, because it's higher, but it went this way. Well, but now you know why. It's totally different. Right? The reason is totally different than why this changes, but you can understand it for the same root, which is the behavior of the electrons. So in a metal, in a semiconductor, this temperature dependence, here I've taken the temperature dependence away because I've doped it. But here, that's the thermal activation into a place of freedom, into a place where they can be free in the conduction band. Here, they're already totally free. So what's happening? Well, when I increase the temperature, I'm increasing the vibrations. You can imagine if these electrons are trying to do their thing, and they're in like a sea of electrons, the last thing I want to do if I'm moving along is to see some big ion moving around. And if it moves more, then it's going to make me more upset and get in my way. That's temperature. But that's why this goes down and not up, right? For metals, the more thermal energy you put in, the more those ions, those positive charges, they're positive, right, are going to interfere with the electrons being free, right? Oh, we are understanding things. We understood why these have. Now, you might say, well, why are these different? That's complicated. Relativity. Not part of this class. But if you want to understand why these are different from each other, they're all really high. Why are they different? It goes beyond the scope of this class, but it's also a very interesting story that has to do with, on the one hand, relativistic effects. Okay. Now, there's another thing, which is that if I go back to that table, and I did this, I really did this a lot. I clicked back and forth between, okay, electrical. Now look up here. Thermal, electrical. Thermal, electrical. And you can click, you go, and you can watch the table and do that for like 5 minutes or so. And what you'll find is almost nothing changes. You can't do that with very many properties, but for metals and those two properties, they're almost identical. Again, it goes back to the C. It goes back to the C because, you know, if you have electrons that are free in a material, you can also, those can carry not just electricity, but those can be the dominant carriers of thermal energy as well. And I'm not going to go into those details, I just want to mention it. So this is actually called the Wiedemann-Franz law, and it basically says for metals that the thermal, let's see, okay, I'll just write it here. Thermal divided by electrical conductivity for both. Conductivities. Okay, I'm putting it in parentheses. It should be thermal conductivity divided by electrical conductivity goes as some constant times the temperature. And look at, so if you look at that, so you can look at it by toggling back and forth and see how similar these are. You can also just plot stuff or find plots of stuff. Here's one, electrical conductivity. This is at some fixed temperature. Orders of magnitude variation, tons and tons of different materials. This is the Wiedemann-Franz law. And now you know that law is simply a result of the fact that these free electrons can carry both electrical, right, their charge, as well as thermal energy. And that the way they carry those are dependent on the material, dependent on the number of electrons and the way they bond and all that. But if they carry it in one way for one, it carries it in the same way for the other. Right? So that's okay. And look at all these things. Now, notice here this word that's used a lot, alloy. 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 These are all, okay, alloy. And I mentioned the word alloy on Wednesday because I said if you wanted to make a good blue LED, you had gallium nitride, but it was a little too high in its band gap, so they alloyed it with other, and that meant mixing in. Well, that is done for metals. That is done for metals in a very wide range. Why? Because the metal properties that you have, you may like some of, but you may not like others. Right? So, like for copper, it's got this really high conductivity, but maybe you don't want it to be so malleable. What does that mean? We'll see in 10 minutes. Malleable, ductile. But so what do? Well, you alloy it, right? And so here's an example. Brass. Well, we know brass, but now you know brass. Now you really know brass. You didn't know brass. You don't know anyone or anything until you see it as an atom and electrons. That is how you know someone. Copper with zinc substituted in a 2-to-1 ratio, copper to zinc, the conductivity drops. Those electrons are not as free, but they're still pretty free. Maybe they're a little more tied up in the bonding, and maybe what you've done by alloying is changed its mechanical properties. Because I kind of want something copper-like, but I want it to have different mechanical properties, so I alloy it. And this is really how we think about materials design. I need something to have, let's say, a certain set of properties. Well, I don't have them all here, and I don't have them all here, but how can I use a combination, right? How can I use a combination to get what I want? Bronze is copper with tin. 4-to-1 ratio copper to tin. Conductivity drops even more. It's not so simple, right? It's not so simple as, oh, if it's 4-to-1, then maybe it's like 20%. No. Because it has to do with what happens to the freedom of these electrons. That's what it has to do with, and that's more complicated. But maybe I've changed the properties in another way that I really like. Well, those are substitutional. Substitutional alloys means I took one of the coppers out and I replaced it with something else. Here's brass with zinc in there. You can also have interstitial alloys. And interstitial alloys, so if we'll be coming back to this when we talk about crystals next week, but alloys, actually when we talk about defects, so you can have substitutional, and you can have interstitial. This is just a preview, interstitial. This is just a preview. We're not going to be testing on this or thinking about this much until we get to actually putting these things in to a crystal later as defects. But right now, I just want to make sure you kind of see them for the first time. Substitutional, interstitial. Why would you want one of those? Well, it depends on what properties you're trying to change. In this case, I really like iron. It's really cheap. It's a cool material, but I need it to be stronger. And that's called steel. And if you just put a little bit of carbon, really not much, like 1% by weight, you can dramatically change the mechanical properties of iron. You can make it a much stronger material. There's a massive, massive range of properties. And part of why metals are so tunable is because of the electron C. Well, I just came across this article, actually, and I thought I'd show you. This was just literally yesterday. Is that yesterday? I thought it was an interesting example. Car wars, steel getting stronger, lighter to curb aluminum rise. Well, see, the thing is that, as you want cars to be lighter, think fuel efficiency or range if it's electric, right? You got to use lighter metals. And aluminum is lighter, but aluminum is more than twice as much as steel. It's a lot lighter, though. So there's a lot of interest in making steel, that's just iron with carbon interstitial, in making steel stronger. And you can see, newest alloy. That's what caught my attention. Newest alloy. They've come up with something to add to iron to make its mechanical properties really, really good at a very, very thin layer, right? Because they need steel to be even stronger in a much thinner layer, otherwise it's too heavy. Right? You got to make it really thin and really strong. Those are going to be alloys. Okay, back to our property list. Now, malleability and ductility. Why are metals malleable and ductile? Well, I thought this was a good place for a video because I think this is a really simple explanation of malleability and ductility as it relates to the electron C. So let's watch this. This is like a minute long.
They violently repel each other, breaking the crystal apart.
That's an ionic crystal.
If you hit a metal with a hammer, it doesn't break, it just dents. Metals are able to deform in response to an applied force. The mobile sea of electrons shields the cations from each other, preventing violent repulsion and allowing the metal to change shape. The most malleable metal is gold. A similar property to the malleability of metals is their ability to be pulled into long, thin wires. We call this ductility. Ionic compounds are not ductile for the same reason they are not malleable in general. If an ionic compound is forced into a long cylinder, it breaks apart because of the repulsion of like ions. In contrast, a metal can be pulled into a long cylindrical shape because the cations can line up, shielded from each other as the fluid-like sea of electrons flows around them.
That's my favorite part.
The most ductile metal...
Fluid-like sea. Oh, the most ductile metal. What is it? We may never know. It's platinum. But see now, okay, now that's I just gave it away. Okay. Ductile, malleable, sea of electrons. Sea of electrons. Because did you see them flowing around? You're moving the atom. That was like a dance thing. That could be like a new dance move that you try out tonight, the sea of electrons dance move. I'm just saying that. So the sea of I'm not going to do it again, but the sea of electrons is able to move around the ions as they're distorting because the metal bond is not so directional. The metal bond is not so directional. Because think about it, what is holding the metal together? It's these interactions between the house and the kids that are roaming all over the place. Is the kid over there or over there? It doesn't matter. Just give me a little bit of positive, a little bit of negative charge so I can feel an attraction. That's the metal. That's why it is so able to deform in the way it does, right? Because those atoms are moving around and the electrons are just kind of there as this happy sea, and the bonding remains. It doesn't break. That's the key. Otherwise, this thing would just crack. So wire pulling, check this one out. You can take a 10 centimeter by 1 centimeter platinum rod, and you can spin that into a wire, and this is done. This is a very thin case for effect, but you can make a 0.0006 millimeter diameter wire, and you get 2777 kilometers of wire. Now, that's because of ductility. The only reason I can get from point A to point B there is because I'm not breaking this apart, and that's how thin I can get. 27 millimeter, diameter when I pull it, and I thought that was a really good example of why this matters. because maybe you've noticed, but wires are really important to us, right? We use them a lot. And so, you just saw a cartoon with electrons. Here's a cartoon that I thought was interesting that shows kind of a wire pulling setup. So now this is,
reducing the diameter.
That's a die.
Further reduction can take place using extra dies. The drawn wire is finally wound on a spool. This transformation elongates the wire. 1 meter of 5.5 millimeter wire rod can be drawn to 30 meters with 1 millimeter diameter, or 484 meters with 0.25 millimeters diameter.
Okay, now that is a cartoon, and I think it's always good when you see cartoons like this. You don't know. Go look up what the real deal is. What does it really look like to draw wires? And I found pretty cool. So this is an actual wire drawing plant, okay? And this is what it looks like. Now, there's no audio here, but I just wanted to show you the magnitude. Those are huge towers that are melting metals to give you this first rod, right? And then it goes through one after the other, and look at it being pulled in at some diameter, and it comes out at a different diameter, right? But I wanted to show you the scope and size of this. Okay, so this is just there's a person, and so you get a sense of the of the size, and then you can also see something when you go visit these factories, right, and I have visited these factories, there's always a lot of this happening. Why? Things are getting really hot, right? When you're spinning things like wire at a very high velocity, things heat up, so you get water all over the place, right? So there's water being sprayed in factories all over the place because you got to keep stuff cool. Or there's water baths that you run these things through, right? And then you got to think about, well, does this thing interact with water? How does the water play a role? It all comes down to the electrons. And once they've actually drawn the wire out over this huge factory, they can actually weave it back together. So I found this. This is the same factory. Now these things here are doing the opposite. So these are huge drums about the size of a person, and each of these got a wire that was drawn, right? And now, again, because of the ductility, you can also move the wires, play with the wires, and you can weave them together. You can weave them right back together into a thread that looks like that, which we all have seen, I think many, many times. All of this processing, all of this manufacturability has to do with the electron C. That's why we have wires. Okay, now, a couple more small points. So we're going to go back to this picture because this is how we started. And this is that 1D, remember that 1D model that we used to introduce band theory, right? And I want to go back to this because what you can see is that, if I think about this as bonding and anti-bonding orbitals all kind of mixed in here, then you can also get a sense, right, just like in the dimers that we made, right? N2, O2, right? Remember NO, bond order, right? It counts how many electrons are in an anti-bonding orbital. Just because it's in an anti-bonding orbital doesn't mean it's not there in the system. It's the same with these metal bands, right? Some of them may be good for bonding, some of them may not. But just like in the dimers, the bond order is related to the strength of that bond. Remember, right? And in NO, it's like a bond order of 2.5. And then if I took an electron out, it actually got stronger. The bonding got stronger. It's the same thing in the case. You can think about this the same way in metals. You have a band. I mean, some of these orbitals are not going to be bonding orbitals, and some of them are going to be much more about the bonding. And so that's going to relate to things like boiling point, right? So like, metals have boiling points too, right? And so if you go back to the periodic table, remember the highest electrical conductivity was here. Well, that had to do with that right there, right? With the position, with the filling of the orbitals to give me the freest electron I can imagine, right? After those d orbitals are filled, that s. But if I'm thinking about whether I filled antibonding orbitals or not, because now I'm thinking about the strength of the bonds, you see a different trend. And you see something that you would expect. First of all, you see a huge variability, but you see that the ones that are strongest, the highest boiling points, are going to be the ones where you fill that band, those bands, roughly halfway, right? And this is also why, in a metallic bond, you've got this enormous range, right? So you've got, it's the weakest for elements like, for elements with near empty valence subshells, right? Valence subshells. I'll say, cesium is an example, or near full. Like, for example, in mercury. Now, mercury is actually a liquid at room temperature because of this, right? There it is. There it is, right? Why? Because remember the beryllium dimer, right? Like I've filled all these electrons in there, and they're causing this really weak bonding, right? This really weak bonding because I had to put all of them into the antibonding orbitals. I couldn't do this trick that right over here, right one column next to it, these guys can have tricks where they, now this is bonding strength. This is not electrical conductivity, right? But here they're filling the D, and then the S is free. Not here. Here they're all filled, bonding and antibonding. No tricks. Now, if you look at the melting temperature, that's why one of the strongest elements would be tungsten, right? Strongest would be, example, tungsten, where you've got a range of the melting point of tungsten, and this is not the same as the boiling point. The melting point of tungsten is 3680 degrees C. That's a liquid at room temperature, and the melting point of cesium is 28 degrees C. Look at that range, and it all has to do with how these electrons are filling the metallic bands. And more than that, because it also has to do with the way the atoms come together, and that is going to be the topic of next week. Now, that would have been a perfect line to end on, because I said the words next week, but I just want to make one more point. I can't stop because there's one more thing I want to show very quickly in 1 minute. And that is, going back to this picture, right? If you're thinking about filling, right? And I've got like my 3s. Remember, I've got like my 3s, okay? And, okay, let's put 2p here. And then 3s and 3p. Now, remember, for metals, for a lot of these metals, what ends up happening is what I showed you before on Wednesday, which is that you get actually an overlap of this. So you get a band that would be the 3s, 3p band. Sodium, magnesium, aluminum, these are all come together like this to form a single band. Now remember, I don't need you to know how to do this. We would tell you if it does this or not, right? We talked about that. I'm not going to ask you to know, how these come together. Do they form a continuous band or not? But in this case, they do for that row. And so I've got 8 electrons, 8 electron capacity in that band per atom. That's the capacity of the band. So now I want to talk about how is this band filled? Well, for sodium, I'm going to fill it 1/8 because it's got just 1 electron that it's putting into that band, right? And for magnesium, right? For magnesium, I'm going to fill it with 2 electrons. And aluminum would be 3, and so on. Okay, so it goes back to the same picture as before. We're filling the bands, but now we've got 10 to the 23rd, 24th atoms, and so we think about filling the bands as you know, what's the occupancy per atom that you could put in there, right? And so I could tell you if I had a mole of sodium, how many electrons I have in this band, right? It's a mole, right? And how did you fill it? And that ties into what I just talked about, which is how that relates to bonding strength. Okay, now we can stop. On Monday, we will start talking about crystals. Have a very good weekend.